The ViewMate ultrasound console is a fully featured intracardiac echocardiography system designed for exceptional real-time image guidance and visualization of anatomic structures. The compact console delivers fast, high-fidelity imaging performance to assist clinicians performing complex electrophysiology and interventional procedures. The ZS3 ultrasound platform consists of two major components. 1. The cart, and 2. Transducers. The cart contains the software-driven imaging electronics and user interfaces. It houses the microprocessor, memory, amplifiers, and power supplies for the microprocessor. It sends electrical currents to and receives electrical impulses from the compatible transducers. The cart performs the calculations involved in processing the data to produce the displayed ultrasound images. The console contains an integrated battery pack that can power the system for up to 1.5 hours of normal use. The battery allows the system to be operated without connection to an active AC power outlet. The backup is automatically kept charged by the DC power suppliers within the system. The battery is charged as needed whenever the ZS3 system is connected to active AC power. This is the circuit breaker switch. When servicing the ZS3 system, always be sure to turn off the AC circuit breaker to remove all power from the unit. Otherwise, make sure to have the circuit breaker turned to the on position to ensure that the battery is charging. Press and release the power button to turn the system on. The system takes approximately 30 seconds to complete the normal power on sequence. Check the ZS3 display to ensure the Zenari startup screen is shown. When initialization is complete, the system is ready for imaging. The ZS3 features a full-sized 19-inch LCD display with monitor-mounted high-fidelity stereo speakers. The integrated front handle allows for quick vertical positioning and transport. The height of the user interface console can be adjusted by squeezing the release lever located inside the right front handle. The multi-transducer port, or MTP, allows up to 3 transducers to be simultaneously connected to the system. You can easily activate any of the transducers connected to the cart. The ViewMate ultrasound console is highly flexible and comes with multiple image modes and transducer options. The available transducers include the following: the P9-3IC transducer, or the ViewFlex Extra ICE catheter for intracardiac echocardiography, the P4-1C phased array transducer for transthoracic echocardiography, or TTE, the P8-3 phased array transducer for transesophageal echocardiography, or TEE, the L8-3 linear array transducer for vascular ultrasound imaging. To begin imaging, connect the selected transducer so that the cable is oriented upward. Rotate the connector locking knob clockwise to lock the connector into the port. For the ViewFlex Extra ICE catheter, there are 2 connections. You must connect the catheter interface module, or SIM, to the console port. Once the connector portion of the catheter is handed off from the sterile field, orient the short and long sections of the connector and plug the catheter connector into the catheter port. To select a transducer, The ViewMate ultrasound console is a fully featured intracardiac echocardiography system designed for exceptional real-time image guidance and visualization of anatomic structures. The compact console delivers fast, high-fidelity imaging performance to assist clinicians performing complex electrophysiology and interventional procedures. The ZS3 ultrasound platform consists of two major components. 1, the cart, and 2, transducers. The cart contains the software-driven imaging electronics and user interfaces. It houses the microprocessor, memory, amplifiers, and power supplies for the microprocessor. It sends electrical currents to and receives electrical impulses from the compatible transducers. The cart performs the calculations involved in processing the data to produce the displayed ultrasound images. The console contains an integrated battery pack that can power the system for up to 1.5 hours of normal use. The battery allows the system to be operated without connection to an active AC power outlet. The backup is automatically kept charged by the DC power suppliers within the system. The battery is charged as needed whenever the ZS3 system is connected to active AC power. This is the circuit breaker switch. When servicing the ZS3 system, always be sure to turn off the AC circuit breaker to remove all power from the unit. Otherwise, make sure to have the circuit breaker turned to the on position to ensure that the battery is charging. Press and release the power button to turn the system on. The system takes approximately 30 seconds to complete the normal power on sequence. Check the ZS3 display to ensure the Zenari startup screen is shown. When initialization is complete, the system is ready for imaging. The ZS3 features a full-sized 19-inch LCD display with monitor-mounted high-fidelity stereo speakers. The integrated front handle allows for quick vertical positioning and transport. The height of the user interface console can be adjusted by squeezing the release lever located inside the right front handle. The multi-transducer port, or MTP, allows up to 3 transducers to be simultaneously connected to the system. You can easily activate any of the transducers connected to the cart. The ViewMate ultrasound console is highly flexible and comes with multiple image modes and transducer options. The available transducers include the following: the P9-3IC transducer, or the ViewFlex Extra ICE catheter for intracardiac echocardiography, the P4-1C phased array transducer for transthoracic echocardiography, or TTE, the P8-3 phased array transducer for transesophageal echocardiography, or TEE, the L8-3 linear array transducer for vascular ultrasound imaging. To begin imaging, connect the selected transducer so that the cable is oriented upward. Rotate the connector locking knob clockwise to lock the connector into the port. For the ViewFlex Extra ICE catheter, there are 2 connections. You must connect the catheter interface module, or SIM, to the console port. Once the connector portion of the catheter is handed off from the sterile field, orient the short and long sections of the connector and plug the catheter connector into the catheter port. To select a transducer, on the keyboard press Transducer to display soft keys for each connected transducer. Then press the soft key for the desired transducer. If you would like to switch to a different transducer, simply reselect the Transducer button and press the soft key for the new desired transducer. To enter patient information for a new study, press New Patient. Enter patient information and select the exam and preset on this screen. Press Freeze to begin imaging. Begin scanning and acquire desired images and video. If you are in an emergency situation and need to start imaging right away, you can edit the patient information after the exam by selecting New Patient and making sure to not close the current exam. To collect images into the patient exam, there are 3 keys that can be configured to either print or store images: Store 1, Store 2, and Print. These can be configured to save and send images to an optional printer, hard drive, DICOM network device, or FTP site. These keys can be configured in System Setup, Archive, Store Print. Any of these keys can be configured for any subset of store print destinations. To review images in the current exam, press Current Exam on the back row of the keyboard. All stored images for the exam will appear. To view an image in large format, point with the cursor and press the Set key. Press Current Exam to exit review and return to live imaging. Once you are done imaging, make sure to properly end the exam by pressing the End Exam button on the keyboard. Then select Yes when the prompt asks if you are sure you want to end the exam. To export exams and the collected media files, connect your device to the corresponding media port on the front of the machine. To export exams, first press Archive on the back row of the keyboard. By default, this shows the list of exams present on the internal hard drive. From this screen, the exams can be viewed, copied, deleted, or exported. Point to the selected exam and press Set. Then click Export at the bottom of the screen. On the next screen, point to Destination. Next, select Options. On the Archive Exam Export Options screen display, select Non-DICOM and then select JPEG or TIFF. Remove the identification of the patient if using for a presentation. Click Apply. Click Export on the next screen and verify export by clicking Yes or No at the prompt. Non-DICOM images can be viewed on a computer and used for a presentation. DICOM images can only be viewed on a DICOM networked device, such as when storing images to a PAX server. Finally, to power off the system, press and release the power button. Thank you for viewing the ViewMate Ultrasound Console Quick Start video guide.
Do you know which Indian pharma company has consistently launched innovative first-in-India products? Presenting MCure Pharmaceuticals. With over 500 scientists, we are pioneers in chirality. We have been making a healthy difference to countless families. With cardiology at our heart, we have strived to give you better products always. Chiral products are complex to develop. They are difficult to manufacture, but their benefits make a difference. A difference for your patients, for you. We are proud to launch our latest chiral development, Exafeb, our indigenously developed rivaroxaban. Developed in-house, manufactured at our state-of-the-art facility at Jammu. This is a WHO GMP certified facility. We conduct quality checks to ensure only the best is delivered. Exafeb complements our chiral cardio portfolio. Exafeb, committed to make a difference in anticoagulation therapy for your patients.
The ViewMate ultrasound console is a fully featured intracardiac echocardiography system designed for exceptional real-time image guidance and visualization of anatomic structures. The compact console delivers fast, high-fidelity imaging performance to assist clinicians performing complex electrophysiology and interventional procedures. The ZS3 ultrasound platform consists of two major components. 1, the cart, and 2, transducers. The cart contains the software-driven imaging electronics and user interfaces. It houses the microprocessor, memory, amplifiers, and power supplies for the microprocessor. It sends electrical currents to and receives electrical impulses from the compatible transducers. The cart performs the calculations involved in processing the data to produce the displayed ultrasound images. The console contains an integrated battery pack that can power the system for up to 1.5 hours of normal use. The battery allows the system to be operated without connection to an active AC power outlet. The backup is automatically kept charged by the DC power suppliers within the system. The battery is charged as needed whenever the ZS3 system is connected to active AC power. This is the circuit breaker switch. When servicing the ZS3 system, always be sure to turn off the AC circuit breaker to remove all power from the unit. Otherwise, make sure to have the circuit breaker turned to the on position to ensure that the battery is charging. Press and release the power button to turn the system on. The system takes approximately 30 seconds to complete the normal power on sequence. Check the ZS3 display to ensure the Zenari startup screen is shown. When initialization is complete, the system is ready for imaging. The ZS3 features a full-size 19-inch LCD display with monitor-mounted high-fidelity stereo speakers. The integrated front handle allows for quick vertical positioning and transport. The height of the user interface console can be adjusted by squeezing the release lever located inside the right front handle. The multi-transducer port, or MTP, allows up to 3 transducers to be simultaneously connected to the system. You can easily activate any of the transducers connected to the cart. The ViewMate ultrasound console is highly flexible and comes with multiple image modes and transducer options. The available transducers include the following: the P9-3IC transducer, or the ViewFlex Extra ICE catheter for intracardiac echocardiography, the P4-1C phased array transducer for transthoracic echocardiography, or TTE, the P8-3 phased array transducer for transesophageal echocardiography, or TEE, the L8-3 linear array transducer for vascular ultrasound imaging. To begin imaging, connect the selected transducer so that the cable is oriented upward. Rotate the connector locking knob clockwise to lock the connector into the port. For the ViewFlex Extra ICE catheter, there are 2 connections. You must connect the catheter interface module, or SIM, to the console port. Once the connector portion of the catheter is handed off from the sterile field, orient the short and long sections of the connector and plug the catheter connector into the catheter port. To select a transducer, on the keyboard press Transducer to display soft keys for each connected transducer. Then press the soft key for the desired transducer. If you would like to switch to a different transducer, simply reselect the Transducer button and press the soft key for the new desired transducer. To enter patient information for a new study, press New Patient. Enter patient information and select the exam and preset on this screen. Press Freeze to begin imaging. Begin scanning and acquire desired images and video. If you are in an emergency situation and need to start imaging right away, you can edit the patient information after the exam by selecting New Patient and making sure to not close the current exam. To collect images into the patient exam, there are 3 keys that can be configured to either print or store images: Store 1, Store 2, and Print. These can be configured to save and send images to an optional printer, hard drive, DICOM network device, or FTP site. These keys can be configured in System Setup, Archive, Store Print. Any of these keys can be configured for any subset of store print destinations. To review images in the current exam, press Current Exam on the back row of the keyboard. All stored images for the exam will appear. To view an image in large format, point with the cursor and press the Set key. Press Current Exam to exit review and return to live imaging. Once you are done imaging, make sure to properly end the exam by pressing the End Exam button on the keyboard. Then select Yes when the prompt asks if you are sure you want to end the exam. To export exams and the collected media files, connect your device to the corresponding media port on the front of the machine. To export exams, first press Archive on the back row of the keyboard. By default, this shows the list of exams present on the internal hard drive. From this screen, the exams can be viewed, copied, deleted, or exported. Point to the selected exam and press Set. Then click Export at the bottom of the screen. On the next screen, point to Destination. Next, select Options. On the Archive Exam Export Options screen display, select Non-DICOM and then select JPEG or TIFF. Remove the identification of the patient if using for a presentation. Click Apply. Click Export on the next screen and verify export by clicking Yes or No at the prompt. Non-DICOM images can be viewed on a computer and used for a presentation. DICOM images can only be viewed on a DICOM networked device, such as when storing images to a PAX server. Finally, to power off the system, press and release the power button. Thank you for viewing the ViewMate Ultrasound Console Quick Start video guide.
Good evening, everybody. Welcome to the beginning of Digital IHRS 2021. We have managed to structure a beautiful and a very educative program which extends through the whole week. Particularly the pre-conference session was the brainchild of Dr. Kalambur Narasimhan, senior most electrophysiologist in the country and a past president of the Indian Heart Rhythm Society. Certain aspects of EP and heart failure, which sometimes don't get discussed in the mainstream conference, needed to be discussed much more widely. And that's how these pre-conference sessions have been constituted. We have really what I call the big daddies of experimental electrophysiology as speakers in this session. And let me quickly introduce them before we get on with the main sessions. I call this as a EP Beyond 2021 session. Some of the things that these speakers have worked on are already incorporated into our routine practice, day-to-day practice, and some things are probably going to come into our practice possibly in a few years from now. And that's how those
recording in progress.
And that's how those topics have been selected. So in this session of EP Beyond 2021, we have 3 speakers. Each of them will have their presentation for 20 minutes and followed by a short discussion with the moderators. So the first talk is about biological pacemakers. How long is the road to the clinic? This will be delivered by Professor Eduardo Marban. Professor Marban is the Mark Siegel Family Foundation Distinguished Professor and Executive Director at the Smith Heart Institute. The Marban lab uses biologically based therapies for cardiac regeneration and biological pacemakers. This is really futuristic, and we all would need to concentrate to really understand what Dr. Marban is doing. has never happened at the IHRS before, and I'm happy that Dr. Marban is with us. The moderator for this session is Dr. Kalambur Narasimhan. This is followed by a topic which is somewhat already into our clinical practice, ECG imaging. Dr. Yoram Rudy is the pioneer of this technique of body surface mapping with ECGs. And I would like to understand from him how this technique can be used to decipher the different arrhythmic substrates in a non-invasive manner. Again, very interesting and probably much more closer to the EP lab. Dr. Yoram Rudy is the director of Cardiac Bioelectricity and Arrhythmia Center and the Fred Snide Distinguished Professor of Engineering, Professor of Biomedical Engineering, Cell Biology and Physiology, Medicine, Radiology and Pediatrics. That's great even to read. The Yoram Rudy lab says the mission of our laboratory is to conduct and research and provide training in the fields of cardiac EP and ECG in an effort to develop better approaches for diagnosis, prevention, and treatment of cardiac arrhythmias and sudden cardiac death. Again, that would be great for the digital IHRS 2021. This session would be moderated by the current Vice President of the Indian Heart Rhythm Society, Dr. Ullas Pandurangi. We would have, not the last but the least, a live presentation on something that is much widely under discussion in EP. That's about atrial fibrillation. The molecular mechanisms of different clinical AF subtypes. Again, I think that would make our understanding of the therapeutics better if we listen with intent to Dr. Stanley Nuttall. Professor Nuttall is from Montreal, Canada. He is the Paul David Chair in Cardiovascular Electrophysiology and Director of the Electrophysiology Research Program at the Montreal Heart Institute. He is the Editor-in-Chief of the Canadian Journal of Cardiology, Associate Editor of Cardiovascular Research, Rhythm Disorders Section, and Editor in JACC. His research focuses on clinically relevant mechanisms of cardiac bioelectricity, and he is as widely published as having more than 650 publications. That's huge. To moderate this session, we have Professor Dr. Mohan Nair from Delhi. Once again, atrial fibrillation is quite close to his heart. So I think all in all, it promises to be a great session. I do not think I should take any time out of these wonderful discussions that we expect in the next 1.5 hours. It would be a pioneering session for the Digital Indian Heart Rhythm Society Conference at 2021. So I would request that we start with the presentation. Is Dr. Narasimhan there already? I haven't seen him on this thing. Sure. So I think we will let Dr. Narasimhan interject during his moderation time. And I think we can start with the first presentation. Biological pacemakers, how long is the road to the clinic, by Professor Eduardo Marban.
Today, I'm going to talk about the biological pacemaker and the trajectory towards the clinic. The field of modern therapy for arrhythmias is marked by drugs, which work sometimes, but just as often they make things worse. Selective tissue destruction by catheter ablation, which is potentially curative for some reentrant arrhythmias, but is still being optimized. And implantable devices, which in the case of pacemakers are palliative. They work well, but the patient is just as sick as they were before the device if the device fails. And for ICDs, there's no prevention of the arrhythmias, but termination. So there's inevitable shocks if needed. Either one involves a lifelong commitment to repeated procedures, significant expense, and rare but potentially catastrophic complications. So we explored either gene therapy or cell therapy for various indications as alternatives to drugs, ablation, or devices. The targets to date for biological therapies include AV block, for which we've engineered a bypass tract atrial fibrillation, where slowing of conduction in RBR was achieved by selective genetic transduction of the AV nodal region. And ventricular tachycardia, where we've used biological approaches to create a substrate modification alternative to ablation. But today, the focus is bradycardia, where we seek to enhance automaticity in some region of the ventricle that, or the heart, that is not automatic normally. In this case, we seek to modify the region of the high septum around the His bundle to achieve antegrade conduction throughout the ventricles by genetic manipulation. Reflecting on the history of electronic pacemakers, starting in the 1950s up until now, there's been progressive miniaturization and optimization. But even though the pacemakers are highly effective, as I mentioned before, they're palliative, not curative. There's the commitment to hardware, and there are certain indications for biological pacing that would be implausible for hardware pacing, such as congenital heart block or chronic infections where hardware is contraindicated. So there is a demonstrable clinical need for a biological pacemaker that would be hardware free, because only a small part of the heart in principle needs to be converted to a pacemaker. Focal delivery of genes or cells is feasible, unlike the situation, for example, in cystic fibrosis, which is a genetic disease in which gene therapy would have to transduce practically every part of the lungs and pancreas in order to be effective. It's easy to quantify the efficacy of this gene therapy approach or cell therapy approach, in the sense that all you need to do is to take the pulse or an electrocardiogram. And if you create a biological pacemaker and it goes too fast or too slowly or works erratically, it can be fixed by ablation and resort back to a hardware alternative. So the conduction system begins with impulse generation in the sinoatrial node, traveling through the AV node and into the His-Purkinje system throughout the ventricles. And it's the separation of this conduction system from atrial and or ventricular myocytes that causes standstill. If the electrical signal fails to conduct into contractile tissue, then the heart is at a standstill. If you look at the electrophysiological signatures at a cellular level of nodal tissue at one extreme here, sinoatrial node, as opposed to ventricular muscle over here, there are several signature differences. The electrical potential of the sinoatrial node is relatively depolarized, and it undergoes these cycles of depolarization dependent on what's called phase 4 depolarization that leads to rhythmic cyclical electrical activity. Ventricular muscle, on the other hand, is highly polarized and has no phase 4 depolarization. In the absence of an external impulse, ventricular muscle would not fire. So what we'd like to do is to convert some part of the ventricle, for example, the septum, into tissue that resembles the sinoatrial node, so that this part of the region becomes, this part of the heart becomes automatic. This is easy to do in PowerPoint, but in biology, one has to devise various ways of making it so. And I'm going to show you evidence that there are ways we can make it so, and then converge upon our preferred method right now. So the first approach we took was to create a poison pill construct that would cripple the KRR2 family of genes within the ventricle, which encodes an ionic current called IK1. And this is a potassium channel, and the reason that we targeted this potassium channel was relatively simple. It is very vigorously expressed within ventricular muscle, but not expressed in sinoatrial node. And we reasoned that its absence in sinoatrial node releases what in essence is an electrical brake mechanism within the ventricular muscle that anchors the membrane potential and keeps it negative. Here, all the other ion channels may suffice to liberate endogenous pacemaker activity if this electrical brake were removed. At least that was our theory. So we created this poison pill construct, which we called KIR 2.1 AAA, put it in an adenoviral vector, and basically created a functional reengineering of the ventricular myocyte as shown here. And this approach, which was the first to create a biological pacemaker de novo, yielded in ventricular myocytes that normally look like this, cyclical spontaneous firing and idioventricular rhythms in vivo. This was the case when we had injected an adenoviral vector containing the 2.1 AAA construct. But if we merely injected an adenovirus that expressed a green fluorescent protein reporter, the electrophysiology of ventricular myocytes was conventional, flat resting potential, no impulse in the absence of external stimulation, and a normal PQRST complex on the electrocardiogram. Another conceptually appealing approach is to create beating embryoid bodies from induced pluripotent stem cells or from human embryonic stem cells, and to implant those embryoid bodies onto ventricular myocytes or into the heart to basically entrain the heart as a pacemaker. We did this in 2005. We stably transduced human embryonic stem cells that had been differentiated in vitro into beating embryoid bodies. We transduced them with green fluorescent protein so we could tell what was human tissue and what wasn't. We put this beating human cardiac mass and transplanted it onto a monolayer of rat heart cells, and we monitored the electrical and mechanical activity. And in so doing, we basically, using this microelectrode mapping system, could prove that the impulse in the monolayer originated with this green cardiac mass, which is a human embryoid body. It's been transduced with GFP. This sets the pace and entrains the surrounding monolayer. We also did this in vivo and showed that it could actually capture the impulse in immunosuppressed guinea pigs. We can also tune the frequency of these induced cellular pacemakers by transducing them with different ion channels. Here, for example, transduction with the HCN pacemaker gene would increase the frequency of beating so that we could create, in principle, tuned frequencies that could be used for different indications. Another approach, which I'd like to tell you about, but which we ultimately decided not to pursue, involved taking a fibroblast and transducing the fibroblast with ionic channel genes, in this case encoding the IF current, the pacemaker current, and again, it's HCN1, and using a chemical cell fusion method to basically make these fibroblasts fuse and create a heterokaryon with endogenous cardiac myocytes. In so doing, delivering the contents of this cell into the myocyte and also fusing the cell membrane so that now this heterokaryon expresses pacemaker channels, which were not there before. This is an example of what this looks like. These are transduced fibroblasts that are loaded with a green dye. And when they fuse with cardiac myocytes, they share the internal green dye with the cardiac myocyte, proving that it's a fused cell heterokaryon, and this now behaves electrically as a single cell. And these single cells, when you fuse an HCN1 expressing fibroblast in vitro with a cardiac myocyte, leads to rhythmic beating, very similar to a nodal cell with a depolarized resting potential and phase 4 depolarization. Unlike the myocytes that are fused simply with a GFP expressing fibroblast, which have a negative resting potential, and in the absence of this stimulus, which you can see witnessed here by a stimulus artifact, would not fire. We did this in vivo as well by injecting fibroblasts focally with polyethylene glycol to induce heterokaryons, and in so doing, we're able to create an idioventricular rhythm and demonstrate that the myocytes so created, the heterokaryons so created, would actually express pacemaker current and spontaneous activity, albeit not perfectly regular spontaneous activity. So we then converge on the approach that we favor now, which is somatic reprogramming. It's actually converting one cell type into another, taking advantage of transcription factor overexpression. In this case, we chose a transcription factor TBX18 that is expressed during intrauterine development and the formation of the sinoatrial node, as I'll show you. And in so doing, basically converted a ventriculomyocyte into a sinoatrial node cell, which we called an ISAN, or induced sinoatrial node cell. That this isn't a cardiac myocyte that's been fooled into somehow overexpressing ion channels or being entrained with exogenous stem cells. It actually creates a phenocopy of sinoatrial node cells within the ventricle. The choice of TBX18 came from studies of the heart development in mice, where at embryonic day 9.5, as the sinoatrial node is being formed, that region transiently expresses a number of transcription factors, including islet-1, SHOX2, and different members of the TBOX family. We tried these individually, and the one that gave us the greatest success in vitro in creating beating cells was TBX18. We created an adenoviral vector and used it to transduce cells first in vitro, where we were gratified to observe that transduction with a construct consisting of TBX18 and independent ribosomal entry site, and then the green fluorescent protein, so that we could tell which cells were transduced. This led to almost total suppression of connexin 43, which is absent in the sinoatrial node region, but transduction just with GFP did not do so. So you can see here visually the presence of ample connexin 43, which is gone in cells that are transduced with TBX18. Instead, the connexin 45 and connexin 40 seem to provide the connections in that region. As you can see here, connexin 43 is selectively suppressed, recapitulating one cardinal feature of the sinoatrial node. But much more trenchant is the observation of what happens when we inject ag TBX18 focally in vivo. This is what normal ventricular myocytes look like. They're large rectangular cells with very clear striations. This is what sinoatrial myocytes look like. There's several clustered together here, but look at this one. It's a long spindly cell, which has only relatively sparse myofibrils. And this is what a ventricular myocyte looks like after it's been transduced with TBX18. There's two of them, but they have this long spindly shape, sparse myofibrils, very similar to a genuine sinoatrial node cell. Electrophysiologically, this is what a sinoatrial myocyte looks like when it's being patch clamped and from the patch clamp in current clamp mode, one is recording spontaneous action potentials. It fires cyclically and has phase 4 depolarization. At the other extreme, this is what a well-behaved normal ventricular myocyte looks like. Only action potentials are triggered externally, and the memory potential is flat and negative at rest. But here's a ventricular myocyte, one of these, that's been transduced with TBX18. It creates a faithful copy of a sinoatrial node myocyte electrophysiologically as well as morphologically. Well, we now have a candidate therapeutic that we've packaged into a viral vector. How do we get that into the heart? And specifically, how do we get it into the region of interest, which is the His bundle high septum. Eugenio Cingolani and we in our lab collectively took an approach involving a NOGA guided, which is a magnetically guided injection catheter. So we could localize it within the heart and inject focally into the region of interest. And by doing so, we were able to create biological pacemakers in the high AV node region in pigs, and show that the mean heart rate was significantly greater than just with a reporter gene, and the dependence on electronic pacemakers, backup pacemaker, was much lower, essentially zero, for at least a week after injection, as opposed to the significant need for backup pacing in an animal that have been injected, or sets of animals that have been injected just with GFP. And if we look closely at the area of injection, we can identify cells within what would otherwise be normal ventricular myocytes that have the spindly shape characteristic of sinoatrial node cells, not seen ever in animals injected only with GFP. And in the ones that, in the tissue area, there's expression of genes that are basically characteristic pattern for the sinoatrial node. So the black here is remote regions not injected. White is the gene injected region. So it's suppression of connexin 43, upregulation of HCN4, the pacemaker gene, and other signature changes, including suppression, as I told you, of this anchor ion channel KIR2.1. Accelerometry studies showed that the animals not only had a higher overall heart rate, but they were able to sustain activity much better than animals that did not have biological pacing. So here's a 24-hour plot of activity in two basically representative animals. One that had been injected with GFP during the waking period from 8 a.m. to about 6 p.m. Had bursts of activity, but the animal was unable to sustain them. Whereas here, pretty much in the entire waking period, the animal was able to sustain high activity, and the heart rate during maximal activity was higher in these animals that have received the active TBX18. So among the questions that we need to answer to address the overall topic here is the how long to the clinic, are the persistence of the benefits in the long term, and also whether you can actually not just prevent heart block, but actually reverse established right ventricular cardiomyopathy related to ectopic pacing electronically. So when we simultaneously induced heart block and TBX18 injection and followed the animals, in this case for 2 months, we had a sustained increase in mean heart rate over those 2 months, and a decrease in the need for backup pacing. Although over time, the need for backup pacing did increase over the 2-month study. So it wasn't a perfect physiological response, but very meaningful in terms of overall benefit. Now, if we allowed the animals to go into heart block and depend largely on right ventricular pacing, and then injected TBX18 into the His bundle area, we were able to increase heart rate and decrease backup pacing in a very established long-term model of heart block. So just to summarize, I've shown you various novel cell and gene-based alternatives to electronic pacemaker. The one we favor for advancing to the clinic is somatic reprogramming, which converts ventricular myocytes to sinoatrial node-like cells. We've developed clinically realistic percutaneous delivery approaches to put genes into the AV junction. So the next steps would be animal testing with clinical rate vector, which we're working hard to develop, and do appropriate regulatory filings with in the US anyway, with the Food and Drug Administration and the Institutional Review Board, and then contemplate first in human trials. And the populations we have in mind for these would be a bridge from one device to another device in pacemaker currents that have hardware infections. So if the infected system is removed, it would be nice to have a cleansing period of, let's say, 2 weeks with antibiotics, in which there's no hardware in the body before you implant a second system. So it's sort of a bridge to device. And the other indication would be in fetuses with congenital AV block refractory to corticosteroid therapy in the third trimester. These infants develop hydrops fetalis with an 80% stillbirth rate. And so this would be a very potent kind of rescue mechanism if we were able to deliver it intrauterine and prevent the drastic consequences of hydrops fetalis. In thinking about whether it's a crazy idea, it's worth reflecting on the development history of automatic implantable cardioverter defibrillators. This is Michel Morawski, a prototype of the first automatic implantable defibrillator, as he called it. And this is an apical lead and a transvenous lead. He invented this device. And in the mid-1970s, when it was first introduced into animals, there was extreme technical difficulty and skepticism of this approach. The initial clinical studies in 3 patients in 1980, published in the New England Journal, were extremely effective in terms of efficacy. The technical difficulty was great, and the patient population was very limited to those with drug refractory ventricular tachycardia. And fast forward to the modern era, where ICDs have become first-line therapy and even just prophylactic for sudden death, and the technical difficulty is quite routine percutaneous approaches. I'd like to acknowledge the people who worked hard on this in my lab and did the pioneering work on TBX-18, including Hee-Chol Cho and Nidhi Kapoor, and the TBX-18 pig studies with Yufeng Hu, James Dawkins, and Eugenio Cingolani, and some funding was obtained from the NIH for this. Thank you for your interest and patience.
Thank you very much, Dr. Marban. It's really breathtaking work that you have done. And as it was said, the true sign of intelligence is not knowledge, but imagination. And you've just forayed into areas, and probably this will become a reality in the years to come. I'll just open this for questions from the people who have joined us.
So Narasimhan, can I start off?
Sure, please.
So I would like to know how soon into the clinical practice?
Well, I've been mistaken on this in the past. The major sticking point right now appears to be not the technology, but not the delivery technology or the concepts, but the clinical grade vector. It's very difficult to generate clinical grade adenoviral vectors that retain the kind of efficacy that we see with research grade vectors. So we're trying to basically repurify the virus and come up with something that is clinical grade material. And as soon as we do that, we'll be able to continue the regulatory discussions that we've had to get into the clinic. So right now, I would say that it'll happen within the next, first in human studies will likely happen within the next 5 years, but not within the next 2 years, something in that general time frame.
So Dr. Marban, I have a question here. Why we should be treating with the biological pacemakers at a stage when the pacemaker is indicated? Why don't we do in a person who is at risk of developing a CHB, and at that stage, you bring in your biological methods to increase the agility or to increase the longevity of the normal conduction. Why? I think that probably is more easier than when there is already a conduction disease set in.
Yeah, no, you make a good point that there's two populations in whom you can imagine a biological pacemaker being useful. One are patients who don't really need a pacemaker for life-saving purposes. It's just there as a, as you might say, an enhancement to exercise capacity, for example. And the other population are ones who desperately need a hardware pacemaker, but for some reason can't get it. And that population, as you know, is rare. So we believe that the automatic implantable defibrillator development story is somewhat instructive, because that, as you know, began with rare cases of drug refractory VT and recurrent sudden deaths and a very niche population, and then became generalizable to a broad audience. So I think we're going to probably need to do the first proof of principle studies in this highly selected population that's very sick and already has conduction system disease, before even thinking about moving on to the larger, potentially more realistic population.
Thank you.
Any other questions?
Yeah, same.
Yeah, Dr. Mohan. Mohan.
Miroski is a good example, but that was the components are mechanical. Here you're putting in components which are biological. And when you have a biological component, as was said by the speaker himself, right now it's short-term, these are short-term studies. We do not know the stability, the reliability, and the response rates at different conditions on long-term, just like in aging or during episodes of fever, infarction, electrolyte imbalance, etc. It's a huge, big step forward, but I think we have a long way to go.
Yeah, I would not disagree. The longest studies we've done are in pigs over 2 months, and this has been published in the Journal of the American College of Cardiology, and there is sustained efficacy over that time. But I believe in planning first in human studies, it would be best to focus on temporary rather than permanent applications.
I think it's extremely important, because these scientific discoveries have a lot of ripple effect. There are several discoveries. For example, this RNA vaccine was dormant for 15 years in Weissman's lab, and suddenly when there was an epidemic, everyone woke up to the reality. So I think in pure science, these things, we may understand the importance of these things years later. We may not even know about it immediately. I thought you were working a bit on initially on stem cells and muscular dystrophy, or what is your, this can be taken to other areas of cardiology?
Yeah, no, it's a it's a different topic, but we do have a paper coming out in the Lancet shortly, reporting the latest clinical trial of cell therapy in patients with advanced Duchenne muscular dystrophy, and the benefits in that population look extraordinary in terms of preservation of heart function and mitigation of the progressive decline in arm function. These are young boys who are wheelchair bound by and large, and we're trying to preserve their arm function in order to enable them to feed themselves and use a joystick and move their wheelchairs, etc. And that was the primary endpoint of this trial. What was innovative about the trial, though, is that it was given intravenously repeatedly, so every 3 months. So we've moved a long way in cell therapy from the concept that we need to deliver cells to the heart with a catheter or with injection, and now we're giving them systemically. For the heart, in that same trial, there was absolute preservation of structure and function over 1 year, which is very different than the natural history of advanced muscular dystrophy, in which there's progressive cardiac decline. So we're very excited about those findings.
Fantastic. This should be more easily treatable if there is some kind of a clear stop codon mutation and a point mutation, isn't it? Rather than in this dystrophin mutation that we had studied. they have been clinically characterized to have Duchenne dystrophy?
The patients that were treated all have genetically demonstrated absence of, well, some kind of genetic
Dystrophin
mutation
and the thing,
in
yeah.
the dystrophin gene that has led to the clinical phenotype of Duchenne muscular dystrophy. But the therapy we're using is completely ignorant of the underlying mutation. It's not specific for any given mutation because we're targeting autoimmunity and inflammation as factors that get recruited in the process of the pathophysiology. It's not a genetic lesion correction, but rather it's addressing the consequences of the genetic disease.
Sure. Any other questions? Now, when the organizers wanted to have a pre-conference workshop, we wanted to hear from the pioneers in each field who have really, these are the areas in electrophysiology which are really, we are looking forward for discoveries which will change the field and the trajectory of how we treat the disease. And thank you, Dr. Marban, for this wonderful lecture. And I hope a lot of youngsters get inspired to take up pure science and research to follow your footsteps. Thank you so very much for sparing your time.
You're
There are
welcome.
no further questions. We'll move on to the next talk. Ashish?
Yeah, sure. I think that fulfilled the aspirations of the scientific committee to listen to Professor Marban and to his pioneering work. Many thanks, Professor Marban. We move on from here to something that is already entered the EP labs from the experimental stages, I guess. And this is about ECG imaging. How does it help to understand the different arrhythmic substrates? And this comes out of the pioneering work of Professor Dr. Yoram Rudy. And again, I think it's for the first time at the IHRS that we are listening to Professor Rudy. Dr. Ullas Pandurangi will moderate this session. Can we have the presentation of Professor Rudy on?
I thank the organizers for the invitation and the opportunity to present to IHRS. The title of my talk is ECGI, or electrocardiographic imaging, helps deciphering different arrhythmic substrates non-invasively. What is the ECGI procedure? What is electrocardiographic imaging? Well, in ECGI, we have a vest of 250 electrodes, and we record 250 electrodes, electrocardiograms simultaneously from the front and the back of the torso. So the entire torso is recorded. And if you pass a line through all of these electrocardiogram, you obtain right here at one instant of time, the potential distribution all around the torso. We'll repeat this every millisecond throughout the cardiac cycle to obtain the entire electrical information. We also push the patient through CT or MRI scan to obtain the position of the electrodes on the body surface and the heart anatomy in the same frame of reference. So we have a 3D construction of the specific patient's anatomy. And then we developed for many years and validated the physics basis and many mathematical procedures and algorithms to marry the two, the electrical information and the anatomical information, and obtain information on the heart surface, on the epicardial surface of the heart. What we obtain is potential distribution from which we can construct electrograms all around the epicardial surface of the heart, and from those compute the activation sequence or isochrones and repolarization patterns. In other words, this is a non-invasive mapping technique that approximates what you would have measured if you were to open the chest, I put a sock with 1,000 electrodes on the surface of the heart, and it's all done non-invasively. I will show some examples of clinical recordings. The first would be post-myocardial infarction, EP substrate, electrophysiological substrates for ventricular tachycardia, or VT. These are references that those who are interested can read more in depth about this example. So the anatomical substrate of myocardial infarction is a scar. And the scar has island of surviving myocardium which generate electrical activity. The propagation of the electrical impulse through the scar is discontinuous. You have one island excited, generating small deflection in the local electrogram, then another, and there are intervals between those. So the activation basically jumps from island to island, and that's reflected in very low level, fractionated multi-deflection electrograms from the scar location. In contrast, away from the scar, there is single deflection, it's very robust and high voltage. You can see the low voltage from the scar electrogram on an expanded scale and easily see the 3 deflections here, 1, 2, and 3. So multi-deflections, low voltages, are signatures of scar electrophysiological substrate. So we assembled all of those together, and this created the red surface that you see here, which is the epicardial electrophysiological substrate associated with an anatomical scar. The green is the scar border zone, which has rare rhythmic properties. Now, these should correspond, of course, and be consistent with the anatomical substrate. And so we compared it to late enhanced gadolinium MRI scans. You can see here the anatomical scar from the gadolinium MRI scan. We then co-registered it with the CT scan and the ECGI procedure. And now you can compare the electrical scar and anatomical substrate, and you can see that the correspondence is very close. Here are some other examples of different anatomies. This is an apical scar, and you can see the electrophysiological substrate corresponds nicely to the apical location and the anatomy of the anatomical scar. Another more complex example is this pattern here of an anatomical scar, and you can see how the electrical scar really is corresponding and is consistent with the anatomical substrate. Another property of scar is lingering electrical activity during sinus rhythm after the major QRS deflection that really reflects slow conduction, lingering conduction through the scar substrate. This slow conduction is after the QRS and is reflected in deflections in the local electrograms that are known as late potentials. You can see them here in those frames, and all of them come from the red substrate here, which is the anatomical scar. So that's consistent also with what we know about the physiology of conduction of the cardiac impulse through the scar. Here, we mapped the substrate during normal sinus rhythm. You can see at the scar, which is here, low-level potentials. In fact, there is a region, like a corridor of higher-level potentials between very low-level potentials islands, which could be the common pathway of this reentry circuit. We recorded during sinus rhythm the substrate, which has low potentials and late potentials, as shown here, all of them coming from the scar. But then we also recorded the VT, and you see that the VT is really anchored at the scar and uses the scar. There is slow conduction into the scar, the common pathway of the double loop reentry shown here in black, here in white. This double loop reentry has a common pathway of slow conduction through the scar, and the scar in sinus rhythm shows low voltages, fractionated electrograms, and late potentials. I will show you here one example of epicardial reentry circuit. Here, there is a scar obtained from SPECT images shown in red, and you can nicely see the rotor or reentry circuit that uses the scar as an anchor. Ablation in this region shown here was successful in terminating the arrhythmia. And I'll show you in animation 4 beats, a VT beat, another VT beat, then it will be interrupted spontaneously by a non-VT beat, and then another VT beat. Here is the first VT beat. You can see nicely the rotor and rotating wavefront. There is activity in the scar now, and then there is exit site and another VT beat. Now it's interrupted by the A beat, which is non-reentrant. And then there will be another exit from here, generator, another VT reentry VT. As we all know, in broad strokes, arrhythmia mechanisms could be divided into 2 categories, reentrant and focal. And I wanted to show an example of a focal reentry, in this case induced in a patient with non-ischemic cardiomyopathy. And this is really an example of classic electrophysiology and the concept of extension of the line of block. So we paced with a train of S1 beats, and you can see that for a particular patient, there is a line of block shown here with the black thick line, and activation has to go around it. And here, this whole region is a region of compromised activity because conduction is slow. You can see the crowding of isochrones. So we can anticipate that this is an Achilles heel of conduction. And if it's already compromised, you compromise it even more by premature beat. And a premature beat is given while excitability is not yet completely recovered. So therefore, excitability is reduced, and what was an Achilles heel now becomes block. And this is the concept of expansion of the line of block shown many times in animal experiments, but this is the first that I know that shows it in detail with ECGI in a human subject. Now activation has to go all around the line of block. It terminates here, and when we let go, the VT beat starts from where the last activity of the pace beat ended. So the fact that it started from where activity ended suggests that the mechanism, this ectopic focal mechanism, and you can see radial spread from this focus, is the mechanism is triggered activity. And I'll show you this in animation as well. Here is the first S1 beat. Another S1 beat starting from the pacing side. Now the S2 premature beat, again from the same location. But now activation has to go all around. You'll see it goes all around, higher up, and ends in this region here. There'll be another one. Now notice how the VT starts from where the last pace beat ended. Right from here where the last pace beat ended. It's another VT beat, and that was sustained. The morphology of the electrogram in this region suggests it's a pure S-wave electrogram and shows that the focus or the source of the arrhythmia is an epicardial location. And finally, The previous examples focused on the role of abnormal activation and conduction, slow conduction, discontinuous conduction through scarce substrate. But abnormal repolarization is really a major source of arrhythmia as well, and it's an arrhythmogenic substrate, notably for hereditary arrhythmias. And I wanted to show one example of that as well. And the example is the long QT syndrome. This is a normal volunteer, and you can see that the entire heart activation recovery intervals, which is a surrogate for local action potential duration, is around 240 and uniform throughout the heart. In marked constant in the long QT syndrome, there are regions in the heart where activation recovery intervals, the action potentials, are greatly prolonged. Now we reach values of 420. So from 240 to 420, it's over 100 milliseconds prolongation of action potential duration. And it neighbors, it's not homogeneous, and it neighbors regions of shorter action potential duration. That creates very steep dispersion of repolarization, very steep gradients of repolarization. And a region like that, as we all know, is conducive to the occurrence of unidirectional block because of the asymmetry of excitability across the line that separates the two regions. So in this region of steep gradient, there'll be unidirectional block and reentry. So the substrate is there, just waiting for a triggering beat to cause reentry to get started. And this is the same in LQT2, LQT3, the different types of LQT. The dispersion in the normal heart maximum is 7 milliseconds per centimeter. In the long QT is greater than 100 milliseconds per centimeter. So 2 orders of magnitude steeper dispersion. And interestingly, the steepness was greater in symptomatic patients, 130 milliseconds per centimeter, versus non-symptomatic or asymptomatic patients, okay, where it was 98 milliseconds per centimeter. So the steepness, the degree of steepness of the gradient of repolarization could be an index for vulnerability for the development of VT and fatal arrhythmias. So this brings my talk to a conclusion. This is a long list that I cannot read, but in black are the major people in my own laboratory who did this work, and in white are clinical collaborations. These are all at Washington University. These are at Case Western Reserve University, and also around the globe, so to speak. So with that, I'll thank you for your attention, and I will open this for discussion and questions.
Thank you, Dr. Rudy. It's wonderful, and congratulations. You will ever be quoted as the pioneer in bringing in this concept of non-invasive electrophysiology to the aid of the ablationists. Before I raise the questions or the concerns which I have, maybe my esteemed colleagues, Nasim and Mohan, if they're around, maybe Ashish, they may actually clarify some of their concerns or their inputs. Narasimhan, Nair.
So if I may start, Dr. Rudy.
Yeah, the first thing is it's fantastic work, and it's already reached the bedside in terms of and it's one or two questions I had is, can you have an intramural reentry which can be picked up by this? Epicardial reentry, you showed an example that there is an epicardial exit. If it's deep within the myocardium and it exits in the epicardium, is there a way of identifying it?
This is a very good question. And there is a theoretical limitation for reconstructing electrical activity in regions of the myocardium that are electrically active. One assumption of this, what's known as the inverse problem, is that there are no sources, no active sources existing between the surface where you measure the potentials, which is the body surface, and the heart surface. But once you penetrate muscle, you have activity and you have active sources. So that is not allowed in principle from the theory of this problem and the physics of it. However, from the epicardial potential distribution and epicardial electrograms, we can say a lot about what's going on in the intramural inside the myocardial wall. And if it's a pure Q wave electrogram, then you know that it's epicardial. If it has a small R wave to precede an S wave, then it has to come from the deeper layers of the myocardium at that point. Also, if you look at the potential distribution as a function of time, because of the rotational anisotropy of myocardial structure, the activation rotates counterclockwise if it goes from epicardium to endocardium, and clockwise if it goes from endocardium to epicardium. So you can also deduce the direction of activation in the intramural layers. We've done a lot of analysis of situations like that, and based on the electrogram morphology, the progression of potentials in time, and the point of initiation and point of termination of the epicardium, we did chart intramural reentrant circuits, as well as circuits that grow through the septum and use the septum as a pathway for reentrant activity. And that was published in, I think, in Circulation and maybe other journals as well. So you cannot directly measure,
but we can infer,
reconstruct in the myocardium, but you can deduce based on interpretation from epicardial alone. Even better, if you have a catheter in the heart inside the cavity, you can then combine endocardial information with epicardial information, and that is even more powerful.
Interesting.
Professor Rudy, if Ashish Nabar here, if I may ask you, what is more important to the occurrence of torsades? Is it the temporal heterogeneity in refractoriness or a spatial heterogeneity in refractoriness? Can the ECGI help us to conclude that?
That's a big question. We have not done temporal alternance. There is the theory that, bottom line, it comes to heterogeneity of repolarization in the tissue in space. So it's the spatial heterogeneity and asymmetry of excitability that is causing the reentry to start. However, this substrate could be either anatomical or morphological or functional. And we know from the work of David Rosenbaum, the late David Rosenbaum was a good friend of mine, unfortunately not with us any longer, but David showed that concordant alternance in time, create heterogeneity of repolarization in space. So they are not separate, they are not unrelated, they are related. And so the mechanism is the heterogeneity in space, but it could be induced by heterogeneity in time, because the heterogeneity in time, the alternans, are heterogeneous in space. So I hope I answered your questions.
Thanks.
Yeah, so if there are no questions, I will.
1 minute to Ulas.
Yes.
Are there any models where you can predict a proarrhythmia by giving say, for example, by the ECGI? Is it more sensitive? I'm sure it's more sensitive in picking up a person who's about to develop toxic, say, torsades or something, you give a D-sotalol and check it out. What happens?
So we did. So, for example, in the long QT that I showed you, there were just out of pure luck about half. Like there were 25 patients in that study. 13 were asymptomatic and 12 were symptomatic. And the dispersion of repolarization was much steeper in the symptomatic group. So that tells you that if you non-invasively, with much larger studies, we can find and define a threshold that will say if the dispersion is greater than a certain number, then vulnerability, the probability for developing VT is higher. And maybe these patients should be prophylactically treated with implanted device. That's one example. We have other examples. We used it also to guide the placement of a pacing lead in biventricular pacing for heart failure. And that has been an important use. And knowing the substrate before you decide where to put your electrode really is very helpful.
So just like measuring the heterogeneity of the activation recovery intervals, are you also concentrating on measuring the heterogeneity in the voltage of the T waves as some measure of torsades?
Yeah, we do. So in the example that I showed you for the low voltage in the scar region was a major determinant of the electrophysiological substrate. So that's an example where voltages are crucial. And we don't measure absolute voltages, but what is important is the comparative voltages around the entire heart. And we show that in a scar region, the voltage, the electrograms, first of all, are fractionated, but also the voltage is much, much lower than in the surrounding tissue. So we've used that to define the electrophysiological substrate of the scar.
No, I was asking about just like.
By the way, we also use in more recent advances, we've also started to, you probably heard about non-invasive ablation using radiotherapy. And so we use radiation now. We define the anatomical scar with MRI. And then within the anatomical scar, we find the region of initiation of the arrhythmia and aim radiation to that location to terminate the arrhythmia, so far with really much success. And there is a very intense work going on now here to understand the biology of it. It's not killing cells, it's not apoptosis, because it happens on a much faster time scale. The arrhythmias practically disappear in the short term, and then even for long term, there is not much recurrence, much lower burden than before the treatment. But the mechanism is not so clear. One thing that was found recently is that the expression levels of sodium channels and the expression levels of connexin 43, okay, is increased by the radiation. But very interesting, the biology of it. And as a result, conduction is improved. And that might be one of the mechanisms that is antiarrhythmic. You need ECGI in order to know where to aim your radiation.
Professor Rudy, I think ultimately what we are looking forward to is ECG imaging, non-invasively get as much information as possible. And you just quoted stereotactic ablation. I think the resolution at this point in time is such that it is going to recognize some amount of a scar.
Yeah.
It's not as much as recognizing some of the regular arrhythmias. for example, an AVNRT, the mechanism, or a pathway mechanism. I just am asking you a question. You are a pioneer. Would there be a day where we would not take our patients to the lab? Would there be a day where we understand the mechanism of the arrhythmia? And would there be a day there can be, you call it an ablation or destroying the substrate, not necessarily by the stereotaxis stereotactic ablation? Could there be a day when the entire tachyarrhythmia is sorted out non-invasively?
So, this is a very complicated question, of course, and it's loaded. And it's hard to speculate about the future. As you know, speculations are dangerous. But one thing I can tell, one benefit of ECGI, I guess we're talking about in the context of ECGI. So as you saw, ECGI can determine non-invasively the mechanism. We can differentiate in most cases between reentry and focal. We can locate the origin of the arrhythmia and the pathway. So that's as much as you can do if you were to open the chest and put a sock over the heart and record from there, but non-invasively. The benefit in terms of arrhythmia mechanism is the fact that the substrate, as you know, is dynamic. It evolves in time. Many of those things are progressive. There could be a second heart attack, and it's a progressive story. And the substrate, just like in case of atrial fibrillation, AF begets AF. The substrate is changing in time, and slowly, if you let the arrhythmia continue, structural remodeling becomes more prominent and takes over from electrical remodeling. The benefit of ECGI is that it's non-invasive, or one of the benefits, and therefore you can do longitudinal studies. You can bring the patient. In my dream and vision, we'll be able to hopefully do this with echo, 3D echo, instead of MRI or CT. Then you could have it in your office, and you'll be able to call the patient back every 3 months and non-invasively simply follow the substrate as it evolves. Yeah, we're talking about speculative vision. This is speculative vision, but I hope it'll happen. Probably not in my lifetime, but that's my hope.
In the current system,
You have been wonderful. Dr. Nair has a question.
it's a continuation of what you asked. In the current system, what is the spatial resolution? Especially when you're looking
resolution in our hands. So, okay, the spatial resolution and the accuracy and how good the method is depends on the details of execution. And in our hands, we've been doing this for, I started developing the method 40 years ago. So it's been in our hands for many years with a lot of experience. We have many algorithms. We know which algorithm to choose for what application. And so we have fantastic results as validated in comparison to, for example, tank torso with an isolated dog heart, where we could have a gold standard to compare. Our resolution with the simplest method that we use, which is the fastest, is about 6 millimeters. That's a very good number. Below 1 centimeter. With better methods like what's called quadratic interpolation to replace linear interpolation, we can go down to 4 millimeters. But that we pay for with computing time. So it's a trade-off. So these things have to evolve, have to develop, and the commercial systems have to become better and better in time. I mean, you don't want to do what we do, which is careful analysis and we take our time and so on. But if you're there in the EP lab, you expect most of it to be done for you automatically. Or another approach, which could be a very good approach, is to do what's done with imaging now, like MRI, do it before anything. So it's the day before the ablation or the treatment, and then take the time to analyze it carefully, and based on that, plan your intervention.
Right.
Yeah, wonderful. Dr. Nair, you have something more to discuss with Professor. I think we can go on and on because that is our dream. We do not want our patients to be in the EP lab to have the diagnostics and to see where the scar is. Your ECG imaging, it's such a boon already. And I only wish it becomes available more widely in the country. Probably, the so-called MRI techniques, PET CT scans, which we are depending upon. But the ECG imaging, if it becomes more popular, I think, we have the picture of the scar in front of us. And
let me add one more thing, that we recently published a paper where we combined, you can combine methodologies. So we did ECGI together with tagged MRI, and that gave us in 25 or 30 normal volunteers the electromechanics of the heart. So we have in the same heart of the same patient the spread of activation, excitation, electrical, followed by the mechanical movement and contraction and then relaxation. So we can see in the same heart the electrical followed by the mechanical activity. So this kind of dual or triple approaches could be used clinically too in the future.
Professor Rudy, wonderful listening to you. There are so many applications, ablations, and now you said even synchronization. Ashish, you may invite the next the pioneer.
Thanks.
Thank you, everyone. Thank you.
Thanks, Ullas. I think we had a great time with Professor Rudy. I wish there was no clock to this meeting and all of us could keep discussing with the masters. But however, we have planned to move on to another lively talk, and I mean it. Atrial fibrillation is the most common arrhythmia that we have to deal with in clinical practice, and a good understanding of the pathogenesis of this arrhythmia in the paroxysmal, persistent, and permanent, as they are classified, might help us to deal with these patients with little more understanding. For this presentation, we have another pioneer in the field, Professor Stanley Nuttall, and Professor Nuttall would discuss the topic with us live. So I would request Professor Nuttall to share his screen and come live, and Professor Mohan Nair to chair this, moderate this session. Professor Nuttall, the floor is yours.
Except that it says host disabled participant screen sharing. So you'll need to enable screen sharing for me to be able to share this presentation.
Yes,
there we go.
This.
Okay. All right, now I've got it. Let's make sure it works. All right, do you see my screen? Do you see full screen view?
Yeah, it's very clear, yeah.
Yes,
Sir,
please.
you will have to present it in a
presentation
slideshow.
I'm sorry, is it in presentation mode?
Yes, sir.
Okay, fine. And do you see my pointer?
Yes, sir. But you'll have to go to slideshow mode.
It's not in presentation mode.
Okay, so swap displays. Let's try that. How's that?
Yes, that's perfect, sir.
Okay, great. So the topic of my presentation today is molecular mechanisms of different clinical AF subtypes. It's a very stimulating topic, and I thank the
So you're muted.
Unmuted?
Yeah, now we can hear you, sir.
Perfect. Okay, fine. I just I took off my video to save internet streaming capability. All right. So I'm talking about molecular mechanisms of different clinical AF subtypes. This slide is a summary of the principal mechanisms involved in AF. And although the slide looks very complicated, I'll go through it step by step. So ectopic firing is a key component of AF mechanisms. It acts as a trigger. And we'll see in a moment how this works. In addition, abnormalities in conduction and refractoriness create a re-entry substrate. And in combination, these two cause AF. The pulmonary veins play a critical role, particularly in paroxysmal AF, where ectopic activity is central. In addition, the re-entry substrate plays a key role in persistent AF, with AF-induced remodeling leading to extrapulmonary vein sources the longer persistent AF lasts. This is a summary of the different components of mechanisms that are involved in ectopic firing: enhanced automaticity, early after depolarizations, and delayed after depolarizations. Critical component mechanisms are increased expression of pacemaker current for enhanced automaticity, outward current loss of function, and inward current gain of function, causing prolonged action potentials and EADs, and changes in calcium handling with spontaneous diastolic calcium releases playing a critical role in producing DADs. In addition, these are modified by underlying risk factors and conditions that particularly lead to conduction and refractoriness abnormalities via fibrosis, changes in connexins, and changes in ion current function. So this is an outline of my overall presentation. I'll be speaking about ectopic activity mechanisms in AF, and then switch to talking about a common underlying molecular mechanism, including a discussion of cardiomyocyte inflammatory signaling in paroxysmal and long-standing persistent AF, as well as in postoperative AF. And then I will talk about the effects of cardiomyocyte inflammatory signal and AF mechanisms. So in discussing ectopic activity mechanisms, I'll be talking about the detailed molecular basis and how it differs in different AF phenotypes. But then I'm going to switch gears and suggest that different AF phenotypes may actually have a common underlying molecular mechanism, which is then modified by the substrate and regulatory components. So this is a slide illustrating atrial ectopic activity actually maintaining AF. This is from a paper in the Journal of Cardiovascular Medicine. We've all seen many patients like this who have very many atrial ectopic beats, develop runs of AF that can last seconds or even minutes, but tend to always self-terminate. So this type of AF is characterized by many atrial premature contractions, short bursts of atrial tachycardia and fibrillation, and in some patients, it virtually never becomes persistent. And this is from Michel Eyseguer's initial paper on pulmonary vein activity in clinical AF. And you'll note that his first cases involved a very particular phenotype where there was very rapid ectopic atrial firing that sometimes degenerated into fibrillatory-like activity, but clearly appeared to be underlined by rapid local ectopic firing from the pulmonary veins. So what are the mechanisms underlying this phenomenon? So as I mentioned in my introduction, spontaneous phase 4 automaticity could conceivably be an underlying mechanism, and in fact was first presented by Dr. Chung, Dennis Chung, in the Journal of Physiology well before Michel Eyseguer's critical paper. However, you'll note that this spontaneous pulmonary vein automaticity was at an extremely slow rate, with the fastest rate about 30 beats per minute, and this is likely not responsible for the clinical phenomenon. Even with adrenergic stimulation, which accelerated the foci, the rate remained under 40 beats per minute. So spontaneous phase 4 automaticity is not a likely candidate. What about early after depolarizations? We studied early after depolarizations in a mouse model of long QT3 syndrome due to gain of function sodium channel mutations and EADs, and we were able to record spontaneous atrial activity in addition to a tendency to produce AF. But this is responsible for, while this is responsible for some focal activity, it's likely a very small percentage of what we see clinically. So spontaneous phase 4 automaticity is likely not involved in clinical focal atrial activity, whereas EADs contribute in some cases, but likely only a minority. This slide shows what we think is probably more likely to be responsible. It's from a paper by Dobromir Dobrev's lab in Circulation, in which they recorded atrial electrical activity from patients in sinus rhythm versus long-standing AF. These are recordings of intracellular calcium, and this is transmembrane potential. The cells were fired at about 1 hertz, I believe. Then the firing was stopped, and in sinus rhythm, the cells remained at their resting potential and didn't show either spontaneous calcium releases or spontaneous depolarizations. Whereas in the long-standing AF patients, we regularly saw both spontaneous calcium releases and spontaneous action potentials that appeared to be triggered by the spontaneous calcium releases. This is a subsequent paper from Dr. Vogt, in which he looked at similar phenomena in patients with paroxysmal AF, and again saw very little spontaneous calcium releases and inward current, this time in control patients, but in patients with a history of paroxysmal AF, saw many spontaneous calcium releases as well as spontaneous inward currents that would trigger after depolarization. So AF patient atria have a tendency to generate spontaneous depolarizing events, known as delayed after depolarizations or DADs, that reach threshold and can trigger PACs. Now, I'm going to go through in some detail the mechanisms underlying delayed after depolarizations, because you need to know that in order to understand the underlying molecular basis. So the key component is a diastolic release of calcium from the ryanodine receptor. So the ryanodine receptor is actually a calcium release channel. The name is a bit unfortunately confusing, but it's a calcium release channel in the sarcoplasmic reticulum. As you know, the sarcoplasmic reticulum is the main cellular calcium store, and its job is to sequester large amounts of calcium and then release it at a critical time when triggered by the action potential, by the calcium entry and the action potential. The calcium in the sarcoplasmic reticulum, which I'm going to call the SR, simply because there's a lot fewer syllables, is taken back up by the sarcoplasmic reticulum calcium ATPase, or calcium pump, which then reloads the SR after systole, pulling the calcium back out of the cytosol to allow relaxation in diastole. Calcium is not normally released in diastole, but certain abnormalities, which I'll discuss in a moment, result in spontaneous calcium release, which is then exchanged for sodium in the extracellular space. So the sodium-calcium exchanger is a membrane, plasma membrane transport mechanism, a sarcolemmal transport mechanism that normally functions to remove the calcium that's entered through the calcium channel during systole. However, when calcium is released in diastole, the sodium-calcium exchanger picks it up and pumps it back out into the extracellular space, but the released calcium is exchanged for sodium in a 3-to-1 ratio. That is 3 sodium ions come in for every calcium ion that's extruded. So that's an inward movement of 3 positive charges in exchange for an outward movement of 2 positive charges with 1 calcium ion. So there's a net inward current of 1 positive ion, a depolarizing current that's generated by each cycle of the exchanger. This electrogenic release, this electrogenic excess entry of positive ions causes an inward current, which is called the transient inward current, that depolarizes the cell and produces DADs. So the key pathophysiological components are the ryanodine receptor, which is the sarcoplasmic reticulum calcium release channel, and which is regulated particularly by phosphorylation, which enhances its activity and tends to cause diastolic calcium leak when excessive. The SR calcium load, which when it's very high can trigger a spontaneous release of calcium from the SR. And finally, the sodium calcium exchanger. So as I mentioned, both in persistent AF and in paroxysmal AF, we see DADs and abnormal calcium handling. However, the nature of the abnormalities is specific to each. So in the long-standing persistent AF patients, we saw ryanodine receptor hyperphosphorylation causing an excess release of calcium in diastole, as well as increased sodium calcium exchanger expression and function. In paroxysmal AF patients, the ryanodine receptor is dysfunctional without hyperphosphorylation, and a major mechanism seems to be an increase in ryanodine receptor expression, which changes its relative quantity compared to other regulators and causes spontaneous calcium releases, as well as an increased calcium load due to increased calcium uptake. So both long-standing persistent AF and paroxysmal AF patients manifest DADs due to abnormal calcium handling, but with distinct mechanisms. And novel mechanistic approaches may be needed to target patient-specific pathophysiology. Secondly, DADs and triggered activity are the principal source of atrial premature contraction generation. So now that I've emphasized the differences in pathophysiology between different forms of AF, now I'm going to try to convince you that in fact there may be some common underlying features which may be clues to improved clinical therapy. And I want to talk about a fascinating area that's coming to the fore over the last 5 years, which is cardiomyocyte inflammatory signaling in AF. Now, we're all very familiar with the notion of inflammation playing a role in all sorts of pathophysiologies, and inflammation is normally understood to be mediated by activated macrophages and other white cells that release cytokines that produce local inflammation. A key component of this is the NLRP3 system. Recently, over the past 5 years, we, in collaboration with several other groups, have found evidence that this system is actually present in cardiomyocytes and might play a critical role in AF. Dr. Hiller-Brown has produced similar evidence for a critical role of cardiomyocyte inflammatory signaling in heart failure at the ventricular level, but I'm not going to deal with that today. So these are the components of inflammatory signaling, which will be relevant to my discussion. There are three critical components which assemble to form the what's called the NLRP3 inflammasome. These include NLRP3 itself, the nucleotide binding domain leucine-rich containing family pyrin domain containing 3, which is the full name, and you can understand why everyone calls it NLRP3. ASC, which is the apoptosis-associated speckle-like protein domain containing a caspase recruitment domain as well as procaspase 1. These assemble to produce the NLRP3 inflammasome. You can see this green oval, which is procaspase 1, the circle, which is ASC, and the orange squares, which represent NLRP3. So these associate to produce an inflammasome. The inflammasome, when activated, will then act on pro-interleukin 1 beta and 18 to produce mature products, interleukin 18 and interleukin 1 beta, which are key inflammatory products involved in inflammation. Two critical components to this include priming as well as activation. So priming refers to an increase in the amounts of these precursors, whereas activation refers to the process whereby they're actively associated into inflammasomes and then produce the active release of cytokines. So the key components that indicate priming, key increases in these components indicate priming are procaspase 1, ASC, and NLRP3, and the presence of interleukin 18 and interleukin 1 beta, as well as the activation product of procaspase 1, which is caspase P120, indicate activation. So now let's look at what happens to these components in patients with AF. So these slides will show the evidence for both priming and activation in AF. So in a dog AF model produced by atrial tachypacing, we saw activation based on increased production of caspase 1P20. This was also seen in mice in a classical now CREM transgenic mouse, which developed spontaneous AF. In AF patients, we saw evidence of activation in both paroxysmal and long-standing persistent AF patients. Increased priming was seen in terms of increased ASC in paroxysmal AF patients and in terms of both ASC and NLRP3 in long-standing AF patients. We also saw evidence of priming in this mouse model. All of these results were obtained in atrial tissue. We then looked at atrial cardiomyocytes and found increased caspase 1P20 indicating activation in patients with paroxysmal AF, increased NLRP3 and ASC indicating increased priming and persistent AF, as well as increased P1P20 indicating activation in patients with chronic AF. And finally, in a canine persistent AF model, we saw both evidence of activation of priming and activation in the cardiomyocytes. So there's evidence of increases in cardiomyocyte NLRP3 inflammasome priming and triggering in AF in various models. What about, all of what I've told you now is specific to paroxysmal and long-standing persistent AF. What about another AF paradigm, postoperative AF, which is a common clinical problem? So again, starting out looking at tissue, there's evidence of increased priming in the whole tissue lysates, as well as increased activation. I haven't spoken about this component yet, but it's gasdermin D, which is a membrane channel that is activated by inflammasome activation. If we then switch to look at human atrial cardiomyocytes from these patients who subsequently developed paroxysmal AF, we see that there's evidence of increased priming in terms of multiple products, as well as evidence of activation, again, from multiple, based on multiple products. Now, these are patients whose atrial tissue and cardiomyocytes were isolated from the time of the OR. And then later on, we analyzed which patients developed spontaneous post-operative AF several days later. So this is actually the substrate for AF occurrence rather than necessarily directly a cause. So cardiomyocyte NLRP3 inflammasome priming and triggering are seen in cells of patients who go on to show AF. So I've shown you that there's evidence that cardiomyocytes have inflammatory signaling activation within them in various clinical forms of AF. What are the effects of cardiomyocyte NLRP3 activation? This work was done by Na Lee's group, along with Zander Ferenc and Dobromir Dobrev, and I was fortunately able to contribute to it a bit as well, in a fascinating mouse model in which Na created cardiomyocyte-restricted NLRP3 activation. So these mice, their only biochemical abnormality is to have NLRP3 activated from the time of birth. And you can see that these mice then develop spontaneous atrial ectopic activity. These are PACs at 3 months, the frequency of which was significantly increased. This is inducible AF at 3 months in these mice. You can see that the incidence of inducible AF was substantially increased, with almost all the mice showing inducible AF, and the ability of these mice to support inducible AF was suppressed by chronic treatment with an organic NLRP3 inhibitor. So cardiomyocyte overexpression of activated NLRP3 produces an AF-promoting substrate for ectopic activity. And what is the underlying molecular mechanism? This slide will illustrate that. So this was optical mapping on these mice. This is a normal P wave arising in the sinus node. This is an ectopic P wave arising from an ectopic focus. And you can see that the incidence of ectopic activity in these isolated optically mapped hearts was substantially increased. This slide shows confocal microscopic images in which spontaneous calcium releases are seen by bright dots. And you can see that the incidence of spontaneous calcium releases was increased at 3 months in these knock-in mice, as was the frequency in mean data. And the underlying pathophysiologic basis, like in our paroxysmal AF patients, seemed to be primarily an increase in ryanodine receptor expression without an increase in phosphorylation. So cardiomyocyte NLRP3 overactivation alters calcium handling and causes atrial ectopic activity. In addition, cardiomyocyte NLRP3 overactivated mice show evidence of structural remodeling. So at 3 months, their atrial weight to tibial length is increased, indicating atrial enlargement. They have increased expression of the transcription factor MEF2C involved with cardiac remodeling, and a decrease in ARCAN 1.4, which is an anti-inflammatory protein. There's an enhancement in the amount of atrial fibrosis and an increased expression of the gene that produces collagen, the procollagen 1A gene, as well as a fibrotic marker, LGAL-S3, so which encodes galactin 3. So cardiomyocyte NLRP3 overactivation causes atrial structural remodeling with prominent fibrosis. So that's fine. We can show that in this specific model, where NLRP3 is overactive in cardiomyocytes, they develop AF. What about in a mouse model that develops spontaneous AF without directly activating NLRP3? So I've already mentioned the CREM transgenic mouse, which is a classical mouse model in which this adrenergic modulator is overexpressed in an activated form. And you can see that there's an increase in these indicators of NLRP3 activity, procaspase 1 and caspase P120. You can see increases in the statistically significant increases overall in their expression levels on Western blot. You can see the incidence of spontaneous AF is enhanced in these spontaneous AF models, and that there's atrial enlargement. What happens if you cross the CREM transgenic mouse with an NLRP3 knockout mouse, so that now NLRP3 is no longer overactivated? You have a decrease in the expression of procaspase 1 and in procaspase P1P20, a decrease in the incidence of spontaneous AF back to baseline levels, and a decrease in left atrial area. So these experiments show that NLRP3 knockdown suppresses AF in CREM mice with an unrelated primary molecular mechanism for AF. And so the NLRP3 inflammasome system that's activated in patients with paroxysmal, persistent, and post-op AF causes a substrate for AF. But then what actually causes AF occurrence? Why does AF happen in the presence of this substrate? Is the substrate itself enough? Well, we know that postoperative AF occurs at about day 3 to 5, at a time when C-reactive protein is overexpressed, pointing to enhanced inflammation. So to look at what happens, we looked at the spontaneous calcium releases, and in patients with control patients and patients that went on to show postoperative AF. So in the control patients, when you challenge them with this inflammatory mediator interleukin-1 beta, there were some spontaneous calcium releases, but a relatively small number, and they were relatively slow. In postoperative AF patients, challenging with interleukin-1 beta produced dramatic increases in the spontaneous calcium releases that were highly significant and accelerated their frequency. So we can conceive of an unifying mechanism in AF patients where cardiac disease and a variety of risk factors, some of which we know about and some of which we may not know about yet, can induce NLRP3 inflammasome priming and/or activation in cardiomyocytes. This causes a tendency to abnormal calcium handling and DADs, which promotes atrial ectopic activity, and also causes atrial fibrosis, which produces a reentrant substrate. We know, of course, that although in these studies we looked specifically at cardiomyocytes, macrophages are prime releasers of NLRP3 inflammasome, and certainly under certain cardiac diseases and systemic risk factors, macrophages are activated in the heart and cause local inflammation. In addition, adipocytes and fibroblasts may also show NLRP3 inflammasome activation and contribute to this substrate. This is a subject we're actively looking at. Atrial activity, of course, may be enhanced independently by cardiac disease and risk factors. We're not arguing that inflammasomes are the only component involved, as can be the reentrant substrate. So enhanced atrial ectopic activity will lead to paroxysmal AF and will also trigger a reentrant substrate to produce persistent AF. Reentry can also, in some patients, contribute to paroxysmal AF. Finally, we need to be aware of the role of acute triggers. Patients who have postoperative AF, as I've shown you, have a substrate in their cardiomyocytes that's present at the moment of surgery, but these patients have not yet had AF. So they obviously have a substrate, but need a trigger, which in the case of postoperative AF is provided by the inflammation that occurs postoperatively. Interestingly, these patients remain at high risk of subsequent AF because they still have that underlying substrate, which may be triggered by the progression of their disease or by other intercurrent factors. So acute triggers like ANS activity changes, vagal enhancement, combined vagosympathetic activity, inflammation from other causes, myocardial ischemia and heart failure, and so on, in the natural history of the disease may trigger AF. So in conclusion, AF results from a complex combination of atrial ectopic activity and reentry with different predominant contributors in different settings. Atrial ectopic activity appears to be primarily due to calcium-related DADs with somewhat different molecular mechanisms in paroxysmal and persistent AF. Cardiomyocyte inflammatory signaling is activated in patients with various forms of AF, and cardiomyocyte inflammatory signaling is sufficient to produce an AF substrate, although an additional triggering factor may be needed, such as post-op inflammation or others. I thank you for your attention and welcome any questions.
Thank you, Dr. Nuttall. That was absolutely awesome. Just captivating and amazing. I can't remember recently having heard of such a wonderful talk on the molecular basis of atrial fibrillation, starting from the changes in movement of channels to inflammatory markers and to the NLRP3 the NLRP3 inflammatory zone. Now, now that we seem to understand more, or you seem to understand a bit more of atrial fibrillation than people, lesser mortals like us, do you see a change in the approach in the next few years to paroxysmal, persistent, and postoperative AFib? Now that you know the cellular mechanisms a little bit more, do you see
Right.
Yeah.
So that, of course, is a fascinating question, and it's really the key question. And I think, as the two previous speakers emphasized, we need to look at the short term, but also at the long-term horizon. So in the short term, I think what's already changing, and it will change the natural history of AF probably a lot more than ablation or new drugs or anything else, is attacking risk factors. And I think one of the key ones that has been shown is a whole range of lifestyle components. And this is from the critical work of Prash Sanders and his colleagues in Australia, who've shown that weight loss, refraining from excess alcohol, refraining from cigarette smoking, controlling diabetes, hypertension, etc., are key components to AF therapy.
Right.
And in fact, there have been some studies which have even shown that patients who were scheduled for ablation, if they were capable of doing important life factor modification, were able to reduce their AF burden to the point that they didn't need it. And other patients who underwent ablation had a much lower recurrence rate if they were able to control their risk factors. So this is and by the way, we're beginning to see that some of these factors act via inflammasome activation. So this is an important short-term change in AF management that we're already seeing, and that I think will have very important long-term consequences. What you're really asking about is whether all of this elegant research can be translated into practical new therapeutics. And the answer to that is, of course, we're not sure. We and others are working on it. We have evidence that's already published and some that we're working on a paper on, showing that the resolution of inflammation can be a key factor, and that possibly resolution promoting substances may be very helpful in atrial fibrillation. Now, I think just to give you a bit of a philosophical perspective from an older man, I won't say an old man, who's seen some things in my time. So I've seen lots of discoveries, many of which I thought would never result in anything. And the truth was, I was right in 99% of cases. But what really mattered is that in 1% of cases, they created a revolutionary breakthrough. So we can't expect each of our discoveries to result in a revolutionary breakthrough. We have to keep on working on new discoveries, realizing that if 1 out of 100, or if we're really lucky, 5 out of 100 will create a paradigm shift, and that will be very, very important. So I think people need to realize that when they look at the kinds of basic research that were presented today.
So Dr. Natarajan, who is a senior electrophysiologist of the Indian Heart Rhythm Society, has a question. I'll just 2 questions, in fact. He says, what are the therapeutic implications of such pathogenetic mechanisms in one patient versus another, depending on differing mechanisms? And are there ECG clues to denote a particular pathogenic mechanism playing a role in a given case of AFib?
Right. So I think there are. Of course, one, I guess, key component that we see very often is whether someone presents with AF that's sustained and that's cardiovertible, which happens in most of the patients we see with recent onset AF, versus patients, and I have a bunch, and all of us, I think, have a bunch, who have many, many AF paroxysms that very rarely become sustained. So I think the second phenotype is more likely due to primarily enhanced automaticity. The first is due to reentrant activity, and that, of course, affects to some extent our approach to management of these patients. As to the key question, can we yet say, based on a patient phenotype, this is the precise treatment that they should get? I think the honest answer to that is no, other than looking again at the different components of their pathophysiology. So sometimes it's more helpful, rather than looking only at the AF, to take a step back and look at the whole clinical picture. And there we can sometimes see reversible or treatable components that are contributing to the AF or may contribute to its progression. And there, I think, we do have a practical chance to intervene today in any given patient. So, for example, one key area, and I know this isn't the question that was really asked, what was asked was about what we see as electrophysiologists. But as electrophysiologists, I think we're very bad at diagnosing obstructive sleep apnea, which is a very common contributor to AF, and that its treatment can be critical to the management of the AF. Most of us are not very good at asking about questions of history that could be a clue to the presence of obstructive sleep apnea. And moreover, a bunch of studies have shown that those aspects of clinical history are not extremely predictive. So we should probably, one critical component of what we should probably be doing is arranging for all of our patients to efficiently have tests for obstructive sleep apnea, and then if they have a significant amount, to manage it. So I know I didn't answer the question in a satisfying way according to the way it was asked. I can't tell you that we can look at the size or the duration of the P wave, or at some sort of signal averaging P wave.
I'm happy that you talked about obstructive sleep apnea, because I think there's an abstract being presented in this meeting on whether we have come to a time where routine screening by polysomnography is a must in all patients with atrial fibrillation, because the amount that we see and the amount that can be done. So,
well, I would be very curious to see that abstract. I hope you can send me a copy of it.
I'll send you a copy.
Thank you. But intuitively, I think it's something that we should be doing routinely.
Absolutely, yes. If Narasimhan
Dr. Nattal, again, thank you for this wonderful lecture. I just had a question that several of these risk factors, you find that some of them have significant significant activation of NLRP and some of them don't. Is there some kind of gain of function of this in some people? Like you see several diabetics and hypertensives. Some of them developed hypertension related atrial fibrillation, diabetes related atrial fibrillation. The thing is, why is that so? Is there a greater degree of activity?
So you were breaking up a little bit, but I think I got the gist of your question. And I switched off my video to try to save bandwidth. So that's a very important question. Why do some individuals that seem very similar develop AF and others don't? And okay. So why do some patients develop AF and others with apparently very similar features don't? And I think there are a multitude of reasons for it, some of which we have a clue to and others we don't. One of them may be the complex regulation of the NLRP3 system, which may vary among individuals. We know that genetics plays a very important role. And so the basis of the genetic contributors is not well understood. Whether some of them modulate the NLRP3 system and whether they do so specifically in cardiomyocytes or other cardiac cells is an interesting subject for further research. We know that a lot of the key genetic factors that have been identified as contributing to AF are transcription factors, and we're still trying to figure out what are the components that they regulate to allow AF to happen or not. Some of them seem to be structural and related to the pulmonary veins, as in the famous chromosome 22 abnormality, but others are unknown, and obviously much further research needs to be done to uncover this.
Thank you.
Ashish and Ulad, if you have any comments, quick comments to make on this before we wrap up, because I think we have already running out of time, although translational and basic medicine is something which you can sit through the night and will never get tired of.
Dr. Nair, I would only say here that what a fantastic beginning to this IHRS 2021 conference. Congratulations to Ashish. You brought the pioneers, and it's just a beginning of our conference, and what a way to begin with. You introduced us to the pioneers, and thank you everyone. It is just as Dr. Narasimhan was telling, this is the way forward. We are going to be looking at how the electrophysiology work evolves. I'm so very glad that I could hear all of you today. Thank you, everyone. Ashish, special thanks to you.
Sure. Thanks, everyone.
Thanks, Ashish.
Thank you, all the organizers.
It was really a great opportunity.
Great talk.
Sure.
Yeah.
It was really
Thank you very much for the opportunity, and hopefully someday we'll be able to do it where we can see each other face to face.
Sure.
Right.
Thank you.
Sure.
Thank you.
Absolutely a robust opportunity to meet these pioneers. I mean, where in an in-person meeting would have got Dr. Marban, Dr. Natel, and Dr. Rudy on the same stage. So I think we all enjoyed this aspect. What was most impressive was the humility which they concluded about the limitations of their work and the hard work, despite the hard work that they have put behind it over 30 to 40 years is what they counted. So that's wonderful. We had more than 350 people attending, and I think in future the younger minds from India, the anatomists, the pathologists, the microbiologists, cardiology clinicians probably would find it interesting to pursue career under the guidance of these giants. Thank you very much. As Dr. Pandurangi said, a great start to Digital IHRS 2021. We meet
Thank you.
15th for another pre-conference workshop, which is a little more closer to the clinical medicine. Thanks, Dr. Rudy. Thanks, Dr. Natel. Thanks, Dr. Marban. And thanks to all the three moderators, Dr. Mohan Nair, Dr. Narasimhan, Dr. Pandurangi.
Thanks.
Thank you.
Thanks, Satish.
Bye-bye.
Good night.
Thank you
Bye.
very
Good night.
much. It was
Bye.
wonderful.
Pleasure.
Good luck with the rest of the meeting.
Thank you.
Thanks, Dr. Rudy.